Welcome back to our lecture series on structural characterization of materials. I am Professor Ashutosh Tiwari from the Department of Material Science and Engineering at the University of Utah. In the previous lecture, we introduced electron microscopy and discussed why electrons are powerful probes for imaging materials at very small length scales. We examined how resolution is defined, why optical microscopy reaches a fundamental limit, and how the short wavelength of electrons enables nanoscale and atomic scale imaging. Today, we take the next step and ask a more fundamental question. How does electron microscopy actually generate images? To answer this, we will focus on electron-matter interactions, the signals they produce, and how those signals ultimately determine image resolution and image quality, particularly in scanning electron microscopy. When an electron beam approaches atoms in a material, three outcomes are possible. First, some electrons remain essentially unaffected and pass through the material without significant interaction. These are the unscattered transmitted electrons shown by central trajectory in the figure. Second, electrons can interact with atoms in the material. When this happens, two fundamentally different types of interactions are possible. If the electron interacts primarily with the atomic nucleus, it is deflected through a large angle while losing little or no energy. This is an elastic collision, shown by the strongly bent trajectory on the right. If, instead, the electron interacts with the electrons of the atom, it loses part of its energy and is deflected through a smaller angle. This is an inelastic collision, shown by the shallow energy loss trajectory on the left. These two interaction types, elastic and inelastic collisions, form the basis for all signal generation in electron microscopy. On this slide, we focus on what physically distinguishes elastic and inelastic collisions at the atomic level. In an elastic collision, the incident electron interacts primarily with the atomic nucleus. Because the nucleus is much more massive than the electron, the interaction changes the direction of the electron but not its energy. As a result, elastic scattering involves large angular deflections with little or no energy loss. In contrast, during an inelastic collision, the incident electron interacts with the electrons of the atom. Part of the electron's kinetic energy is transferred to the specimen through excitation or ionization processes. The scattered electron therefore exists with reduced energy and typically only a small change in direction. The relative probability of elastic versus inelastic scattering depends strongly on the atomic number Z of the specimen. Materials with higher atomic number have a stronger nuclear scattering, making elastic collisions more likely. This dependence on atomic number becomes critically important later, as it directly underpins compositional contrast mechanisms in electron microscopy. Now that we understand the fundamental interaction mechanisms, we can ask a practical question. What energies do the emitted signals actually have? In scanning electron microscopy, different signals span very different energy ranges, and this difference in energy directly determines where the signal originates and what information it carries. Secondary electrons have very low energies, typically below about 50 electron volts. Because of this low energy, only electrons generated extremely close to the surface can escape. This is why secondary electrons are highly surface sensitive and are primarily used for topographic imaging. Backscattered electrons, in contrast, retain a large fraction of the incident beam energy, often 80% or more of the primary electron energy. Their higher energy allows them to escape from deeper regions of the specimen, making them sensitive to atomic number and compositional contrast. Characteristic X-rays lie in the kilo-electron volt range, typically from a few hundred electron volts up to tens of kilo-electron volts. These higher energies allow X-rays to escape from relatively large interaction volumes, which is why they provide bulk chemical information rather than surface detail. Finally, Auger electrons are low-energy electrons produced through electron relaxation processes following inner shell ionization. Because their energies are very low, they can escape only from the top few atomic layers, making them extremely surface sensitive. Across all of these signals, the same principles applies. The energy of the emitted signal controls how far it can escape from the material and therefore what type of structural, compositional or surface information it provides. We now begin with secondary electrons, which are the most commonly used signal for imaging in scanning electron microscopy. Secondary electrons are generated through inelastic collisions, where the incident electron transfers parts of its energy to the electrons of the specimen. As a result, secondary electrons have very low energies, typically less than about 50 electron volts. Because of this low energy, secondary electrons can escape only from a very shallow region near the surface on the order of 1 to a few nanometers. Any secondary electrons generated deeper in the material lose energy through scattering and cannot escape. This extremely small escape depth is what makes secondary electrons highly surface sensitive. They carry detailed information about surface morphology, revealing fine features such as edges, steps, grain boundaries, and surface roughness. As we saw in the previous lecture, this is why secondary electron imaging is the primary mode used for high-resolution topographic imaging in SEM. Their low energy limits chemical information, but it provides excellent spatial resolution for surface structure. Understanding the origin and energy of secondary electrons is essential because it explains both their strengths, high surface sensitivity, and their limitations, which we will contrast next with other SEM signals. We now turn to backscattered electrons, which arise from a very different interaction mechanism than secondary electrons. Backscattered electrons are produced by elastic collisions, where the incident electron interacts primarily with the atomic nucleus. Because there is little energy transfer in an elastic collision, these electrons retain a large fraction of the original beam energy, typically 80% or more of the primary electron energy. Their high energy allows backscattered electrons to escape from much deeper regions within the specimen compared to secondary electrons. As a result, BSE images are less sensitive to fine surface detail but are strongly influenced by the composition of the material. A key feature of the backscattered electron is that their yield depends on the atomic number Z of the specimen. Heavier elements have a stronger nuclear electric fields, which increases the probability of elastic scattering and leads to a higher backscattered electron signal. This produces what is known as Z contrast. Regions containing higher Z elements appear brighter, while lower Z regions appear darker in BSE images. Because of this, backscattered electrons are particularly useful for compositional imaging, phase identification, and distinguishing materials with different average atomic numbers. In contrast to secondary electrons, which emphasize surface topography, Backscattered electrons emphasize material contrast, making the two signals highly complementary in SEM imaging. Another important signal generated in the SEM is X-rays, which are central to elemental analysis. X-rays are produced through a process known as inner shell ionization. During an inelastic collision, the incident electron can eject a tightly bound core shell electron from an atom, leaving behind an electronic vacancy. This vacancy is unstable. An electron from a higher energy shell then drops down to fill the empty state, and the energy difference between these two shells is released as an X-ray photon. Because atomic energy levels are unique to each element, the emitted X-rays have characteristic energies that allow us to identify which elements are present in the specimen. These X-ray energies are always lower than the energy of the primary electron beam, since they originate from internal atomic transitions. X-rays typically escape from much deeper regions of the material than secondary or backscattered electrons. As a result, X-ray signals provide bulk compositional information rather than fine surface detail. This is the physical basis of energy dispersive X-ray spectroscopy or EDEX, which enables elemental analysis directly within the scanning electron microscope. Compared to SE and BSE imaging, X-ray analysis sacrifices spatial resolution, but provides direct chemical information, making it an essential complementary technique. All the electrons are another signal that results from inner shell ionization, but they differ fundamentally from X-rays in how the atom relaxes. After a core-level electron is removed, the excess energy does not always leave the atom as an X-ray photon. Instead, that energy can be transferred to another electron, which is then emitted from the atom as an Auger electron. Auger electrons have very low kinetic energies, typically a few hundred electron volts or less. Because of this low energy, they can escape from the top of the top few nanometers of the surface, usually around 2 to 3 nanometers. This extremely small escape depth makes Auger electrons highly surface sensitive. At the same time, their energies are element specific, allowing chemical identification of surface species. These properties form the basis of Auger electron spectroscopy or AES, which is widely used for surface chemistry, contamination analysis, and thin film characterization. Compared to X-ray analysis, Auger spectroscopy probes a much smaller volume, making it ideal for studying surface composition rather than bulk chemistry. In scanning electron microscopy, image resolution is not determined only by how finely the electron beam is focused. Instead, it is fundamentally controlled by the size of the region from which the detected signal is generated. If a signal originates from a very small volume, fine spatial details are preserved. If it originates from a larger volume, information from neighboring regions is averaged and spatial resolution is reduced. This is why secondary electrons provide the highest resolution in SEM. They are generated and escape from an extremely shallow surface region, allowing very fine surface features to be resolved. Backscattered electrons originate from deeper within the specimen. Their larger generation volume leads to lower spatial resolution, but they provide a strong compositional contrast. X-rays are generated over the largest interaction volume. As a result, X-ray signals offer excellent chemical specificity, but the lowest spatial resolution. The key takeaway is that SEM resolution is signal dependent. By choosing which signal to detect, we directly choose the balance between spatial resolution, compositional information, and sampling depth. The region from which the SEM signal originates is known as the interaction volume, and its size directly controls image resolution. Several experimental and material parameters determine how large this interaction volume becomes. First, the primary beam diameter sets the initial lateral size of the interaction. A tightly focused beam produces a smaller interaction region, while a broader beam spreads interactions over a larger area. Second, the accelerating voltage strongly affects penetration depth. Higher beam energies allow electrons to travel deeper into the specimen, increasing the interaction volume. Lower voltages confine interactions closer to the surface, which can improve surface-sensitive resolution. Third, the atomic number of the specimen plays a major role. High Z materials scatter electrons more strongly, limiting penetration and producing a smaller interaction volume. Low Z materials allow deeper penetration, resulting in a larger volume and reduced spatial resolution. Finally, surface coatings such as thin conductive layer used to prevent charging also influence where signals are generated. Although coatings are typically very thin, they can modify secondary electron emission and affect surface sensitivity. Together, these factors determine how large the signal generating region is and therefore how much spatial resolution can be resolved in an SEM image. This figure illustrates how the interaction volume changes with both accelerating voltage and atomic number. Let us start with the left side, which shows a low Z material. At low beam energy, the interaction volume is relatively shallow, but it still spreads laterally because low Z atoms scatter electrons weakly. When the beam energy is increased, electrons penetrate much deeper, producing a large interaction volume and reducing spatial resolution. Now look at the right side, which shows a high Z material. Even at the same beam energy, the interaction volume is much smaller. High Z atoms scatter electrons more strongly, limiting penetration and confining interactions closer to the surface. Comparing top to down, increasing accelerating voltage always increases penetration depth. Comparing left to right, increasing atomic number always reduces the interaction volume. The key takeaway is that accelerating voltage and atomic number work together to control where the signals are generated. This directly determines which signals dominate and ultimately sets the resolution and contrast of SEM images. This slide explains why interaction volume is the fundamental limiter of resolution in SEM. When the excitation volume is small, each feature on the surface produces its own localized signal. As a result, closely spaced features remain distinguishable and fine details are clearly resolved. As the interaction volume grows, signals are generated from a larger region beneath the surface. If two features lie within the same excitation volume, their signals begin to overlap. Once signals overlap, the microscope can no longer assign them to individual features. Even if the beam itself is finally focused, overlapping signal generation leads to a loss of spatial resolution. This is why improving SEM resolution is not only about beam size, it is fundamentally about controlling where signals are generated. In addition to interaction volume size, beam shape plays a critical role in determining SEM resolution. For optimal imaging, the electron probe at the specimen surface should be circular and symmetric. A circular probe produces a well-defined, localized interaction region, allowing features to be resolved equally well in all directions. When the beam suffers from astigmatism, it becomes elongated rather than circular. This means the interaction region is stretched along one direction, causing features to appear sharp in one orientation but blurred in the perpendicular direction. Astigmatism does not change the physics of the signal generation, but it effectively increases overlap between neighboring interaction regions along a preferred axis. This result is a directional loss of resolution. Even when accelerating voltage and detector choice are optimized, this is why beam stagnation is a routine and essential step in SEM alignment before acquiring high-resolution images. In practice, a scanning electron microscope can be operated in several distinct modes, depending on what type of information is most important. In resolution mode, the microscope is optimized to produce the smallest possible probe at the specimen surface. This mode prioritizes fine spatial detail and is typically used for high-resolution imaging of surface features. In high current mode, the beam current is increased to generate stronger signals. This improves signal-to-noise ratio and is especially useful for analytical techniques such as X-ray spectroscopy, where sufficient signal intensity is critical. In depth of focus mode, operating conditions are adjusted to maximize the range of heights that remain in focus simultaneously. This mode is particularly useful for rough or topographically complex samples where three-dimensional morphology is important. In low voltage mode, the accelerating voltage is reduced to limit penetration depth. This confines interactions closer to the surface, improves surface sensitivity, and reduces charging or beam damage in sensitive materials. Each operating mode represents a different balance between resolution, signal strength, depth sensitivity, and sample stability. Understanding these modes allows the users to select appropriate conditions for the specific imaging or analysis task. All SEM imaging conditions ultimately reduce to a small set of parameters that the microscopist can control directly. The beam diameter determines how finely the electron probe is focused at the specimen surface. A smaller beam diameter improves spatial resolution, while a larger beam reduces resolution but increases signal strength. The probe current controls how many electrons strike the specimen per unit time. Higher current improves signal intensity and signal-to-noise ratio, but often requires a larger probe size, leading to a trade-off with resolution. The convergence angle describes how strongly the beam is focused as it approaches the specimen. Larger convergence angles allow tighter focusing but can increase aberrations, while smaller angles improve depth of the focus at the expense of probe size. The accelerating voltage sets the electron energy and strongly influences penetration depth and interaction volume. Lower voltages confine interactions near the surface, while higher voltages increase penetration and signal generation from deeper regions. Every SEM image reflects a balance among these four parameters. Effective microscopy requires adjusting them together rather than optimizing any single parameter in isolation. Resolution mode is used when the primary goal is to image fine structural details. In this mode, the microscope is adjusted to produce the smallest possible electron probe at the specimen surface. Because spatial resolution is directly tied to probe size, minimizing the probe diameter is essential for resolving closely spaced features. Resolution mode becomes especially important at high magnifications, typically above 10,000 times, where even a small increase in probe size can noticeably degrade image sharpness. However, reducing probe size often reduces beam current. To form a usable image, there must still be enough electrons reaching the detector to provide adequate signal and contrast. As a result, resolution mode always involves a balance. The probe must be small enough to resolve fine details, but it still carry sufficient current to make those details visible. This trade-off is central to high magnification SEM imaging and explains why resolution mode requires careful alignment and optimization. High current mode is used when the primary challenge is signal strength rather than spatial resolution. In this mode, the microscope is adjusted to increase the probe current, allowing more electrons to interact with the specimen and generate stronger signals at the detector. A higher probe current improves the signal to noise ratio, making images smoother and more stable, especially at low magnification or when using analytical detectors such as X-ray spectrometers. However, increasing probe current generally requires a larger probe size. As a result, high current operation does not improve resolution and can in fact reduce it. This highlights an important principle in SEM operation. A strong signal does not automatically imply high spatial resolution. High current mode is therefore best suited for applications where image stability, contrast, or analytical signal strength are more important than resolving the smallest possible features. Depth of focus mode in SEM is controlled primarily by the probe convergence angle, denoted here as alpha. When the convergence angle is made small, the electron beam approaches the surface more nearly parallel. As a result, the beam diameter changes only gradually as a function of vertical position. This means the beam remains effectively focused over a large height range, allowing surface features at different elevations to appear sharp at the same time. The images at the bottom illustrate this effect clearly. On the left, a relatively large convergence angle, about 15 milliradians, produces a shallow depth of focus. Only part of the surface appears sharp. On the right, when the convergence angle is reduced to about 1 milliradian, the depth of focus increases dramatically, and much more of the three-dimensional surface remain in focus simultaneously. This mode is particularly useful for imaging rough surfaces, powders, porous materials, and fracture morphology where height variations are significant. However, there is an important trade-off. Reducing the convergence angle increases the effective probe size, which leads to a loss of lateral resolution. Depth of focus mode, therefore, prioritizes three-dimensional clarity over the ability to resolve the smallest surface details. Low voltage mode is used when the primary goal is surface sensitive imaging. In this mode, the accelerating voltage is kept low, typically 5 kV or below. Lowering the beam energy limits how far electrons can penetrate into the material, which produces a shallow interaction volume confined close to the surface. Because most of the detected signal originates from this near surface region, surface features are emphasized while contributions from deeper layers are strongly reduced. This makes low voltage imaging especially useful for studying thin films, surface coating, fine topography, and delicate or beam-sensitive materials. The images shown here illustrate this effect clearly. On the left, the image acquired at 5 kV shows enhanced surface detail, with sharper contrast at the edges and finer texture visible across the surface. On the right, the image acquired at 15 kV appears smoother and less surface specific because the higher energy electrons penetrate deeper into the sample, increasing the contribution from subsurface regions. By reducing the accelerating voltage, we effectively suppress these deeper signals and improve true surface contrast. However, there is a trade-off. Lower beam energy also reduces signal strength, which can increase noise and may require careful optimization of probe current and detector settings. Low voltage mode, therefore, represents a deliberate choice. It sacrifices penetration depth and signal intensity in exchange for enhanced surface sensitivity and improved surface-specific resolution. As we wrap up this lecture, we can now see how the physics of electron-matter interaction directly guides SEM imaging strategy. The first key idea is that the image resolution is controlled by the origin of the detected signal. Signals generated very close to the surface, such as secondary electrons, provide the highest spatial resolution, while signals originating from deeper regions inherently limit how finely details can be resolved. The second major factor is the accelerating voltage, which determines the size and depth of the interaction volume. Lower voltages confine interactions near the surface, enhancing surface sensitivity, whereas higher voltages increase penetration depth and subsurface contribution. Finally, SEM image quality is always the result of a balance, not a single optimized parameter. Improving resolution may reduce signal strength. Increasing signal strength may compromise resolution. Enhancing depth of focus often comes at the expense of lateral detail. Effective SEM imaging therefore requires understanding these trade-offs and deliberately choosing operating conditions that best match the scientific or engineering question being addressed.